All right, so we're going to end the first day of the cardiorespiratory system talking about cardiac output. Okay, so three objectives, and actually there's a fourth one that I don't have here, where we're going to talk about torsion and how that affects filling of the heart. Okay, that'll be on your list of objectives. I just don't have it here. So cardiac output. Hopefully you all are aware from your physiology class. It's just how much blood leaves the heart. Okay, it's flow, which is volume per time. Okay, so in this case, it's liters of blood per minute. Really easy to calculate. Heart rate times stroke volume. Remember, the heart, you can only really change two things about it. You can change how often it contracts and how hard it contracts. You can either speed up, slow down, or have larger or smaller contractions. Okay, and so that's really all the heart does. And obviously it's more complicated than that, but that's kind of what we're looking at here. So we're going to look at, we have already talked about heart rate. We talked about intrinsic and extrinsic control. So we're going to talk about stroke volume. And we're going to talk about it in terms of diastole and then systole. Okay, so diastole, well, first of all, with stroke volume, just to be clear, it's how much blood leaves the heart every contraction. And so this is affected by a couple of things during diastole. One is preload, and preload is the pressure that's in the heart before contraction. This corresponds with end-diastolic volume. So, and what's causing the pressure when the heart's relaxed? As I talked about on the previous video, pressure in the heart is caused by one of two things: how hard the heart's contracting and how much blood is in the heart. Well, if the heart's relaxing, because that's what's going on during diastole, the contraction's not doing anything because there's no contraction, so it's all about blood volume. Now, the amount of blood that enters the heart, that's affected by many things, one of which is, well, how much time does it have to fill up? The greater the filling time, the more blood will likely be in the heart. Now, it's not that simple, and we'll talk about that more when we get to exercise. But generally speaking, as filling time goes up, so does stroke volume. As filling time goes down, so does stroke volume, or so does preload. Then on the flip side, we've got systole. Okay, and so this is where we get into ejection fraction. And ejection fraction is just the percentage of blood that exits the heart during contraction. Normally, it's about 60%. You never have 100% ejection fraction. And so anywhere from 50 to 60% is normal, healthy, life's good. Okay, now ejection fraction is affected by afterload. And so afterload is essentially aortic pressure. It's the pressure that the heart has to contract against, and specifically the ventricle, to get blood to leave. Okay, and it's also affected by how much time the heart is in systole. So the faster it contracts, there's less time, or the more often it contracts, there's less time that it's in systole, which makes it more difficult to get blood out. And so you would think that as systole decreases in time, that stroke volume would go down. That's true, and it's also not true because, well, when we're exercising, we have a higher heart rate, which decreases the time the heart's in systole, but our stroke volume actually increases. And we're going to talk about that a little bit in just a second, and we'll talk about it more when we get into the exercise portion of this unit. Okay? And so this leads to torsion. Okay, so torsion is just twisting. So here we've got Chubby Checker doing the twist. Okay, and so you might not know this. I don't talk about it in my physiology class. I'm sure that there are people that do. But when the heart contracts, it twists. Now, during exercise, that filling time is reduced, and this should decrease preload and ultimately decrease stroke volume. If you've got less time for the heart to fill up, then there's going to be less blood in the heart, which means less blood can be ejected. All right? And so what actually happens is that increased contraction strength actually leads to an increase in filling. And the way that this works is it creates a pressure gradient. So when your heart contracts, it actually twists, similar to what happens as shown by this picture here, when you wring out a towel. Okay? So what happens is the twisting motion is similar. Everything about it other than this is different. But when you contract, or when your heart contracts, this wringing motion causes energy to be stored. Okay, think about it kind of like the stretch shortening cycle. It's not the same thing, but it's kind of that idea. We're having a concentric contraction and we're storing energy. So what happens is when that heart relaxes, that energy is released. Muscle fibers recoil, and that creates a pressure gradient that pulls blood into the ventricle from the atria. Okay? And so as a result, we're basically sucking blood into the ventricle from the atria. And this is really important during exercise because we need everything. We need to take advantage of every resource that we've got to increase preload, to increase getting blood into the ventricle. And so as we exercise, we actually are able to store more energy during these contractions. Okay? Now, there are other things that we're going to talk about that will also contribute to having an increased stroke volume despite the fact that heart rate goes up during exercise.